Morning, everyone. So it's my pleasure to host a seminar at SKKU. So my name is Song Kim from Semiconductor Engineers Engineering. Today we have a seminar on DRAM security and RowHammer. So the title of the seminar is Mitigating and Breaking RowHammer in Modern DRAM-based Systems. And the speaker of this talk is Abdullah Jirai. So Jirai is a tenure track faculty member at CISPA and is looking forward to hire young researchers around the world at various levels. So if you are interested, please remain in this room after the presentation, have some short chats. And Jirai's research interests spans over high performance, energy efficient, and secure computer architecture, aiming for robust and sustainable scale systems. His research is published in major conferences including HPCA, Micro, DSN, ISCA, and Usenet Security. So a couple of days, he received a SIG Micro Outstanding Dissertation Award. So please congratulations him with applause.
Thank you. Thank you.
And without further ado, so let's hear what
Yeah, thank you very much for your kind introduction. So do I need to use microphone or can you hear me at the back? Okay, yeah. Okay, I'll just stay here just to be sure. Okay. Okay, good. So yeah, my name is Giray. The last name, don't bother with that. It's a weird Turkish name. So you can reach me at this simple email address, giray@cispa.de. And I will start with a bit more self-introduction. So this is me. I'm a tenure track faculty at CISPA. And I got my PhD from ETH Zurich in 2024. And I've been doing research in the software research group since about like 2016. So spent quite some time there. And before that, I was in Turkey, and then I spent some time in the US as well. And my research interests are mostly in computer architecture, memory subsystem, hardware security, dependability, sustainability, hardware-software cooperation, testing, verification, the list goes on. Okay, yeah, so I just started my new lab like in this part of the Europe. So this is Germany, and then we have Luxembourg over there, France over there. So this is where CISPA is, and geographically, I mean. It's a non-university research body in Germany. If you're familiar with the other universities like Max Planck, Leibniz, it's similar institute called Helmholtz, and Helmholtz has a center over there called CISPA, focusing on information security. Okay, and this is where CISPA is on CS rankings. If you filter it purely for computer security, so it's really focused on that. And if you also include computer architecture, then it goes down. So we need to fix that. But it's not the goal, of course. So for that, with that, I am looking for motivated researchers at different levels, like intern, master student, PhD student. So please talk to me after the talk if you're interested. So this is my main interest, secure and sustainable system scaling. When I say scaling, I mean scaling in two aspects. One of them is manufacturing technology scaling, so that we can have higher performance in our devices and we can have low energy consumption. This is important for sustainability, of course. And it brings us some circuit level failure mechanisms and mitigations of those mechanisms incur high hardware complexity, high energy consumption, reduced availability of the device. So it works against the goal of performance and energy efficiency, right? The other aspect of scaling I'm interested in is scaling out systems in a distributed manner so that we have lower cost of ownership and we have dynamic scaling on demand, which are really good for like many use cases today. And it comes with security and privacy concerns, of course, that are not, a bit overlooked so far. So I'd like to address them. So this is my goal. Systems, I want to enable this. Systems should scale securely and sustainably as chips get denser and many users share systems. And okay, so this is my high-level goal. And then I started pursuing this goal in the memory domain because memory has security issues. I'll talk about RowHammer a lot. And also energy issues in systems today. So, okay, with that, yeah, this is my personal journey towards secure and sustainable system scaling. I started looking into memory access latency, memory energy consumption, and then I moved to this phenomenon called disturbance that I will talk a lot about today. And then recently we focused on more of like improving the availability of data and resources while we have these disturbance problems. And going forward, we have some directions like hardware, software co-design, data-centric security, and better understanding of hardware failures by conducting real experiments on real chips. Okay. So I'll talk about memory isolation. I'm getting into the topic now. So imagine that this is your memory and you perform an access to a memory location. And for some reason, you observe a bit of data changing in some other location as a result of your access. So you do not want this to happen because it causes data loss or corruption. It can compromise your application's correctness. It can be used against you to leak your private information or even to take over your computer. And when this happens, data integrity and confidentiality issues may emerge. And as a rule of thumb, we want this concept called memory isolation, meaning that an access to memory address should not cause some unintended side effects on other locations. Unfortunately, memory isolation is difficult today in modern memory chips, and here's why. As the main memory, we use DRAM technology, dynamic random access memory. Excuse me. And this is how a bit of DRAM, bit of data is stored inside the DRAM chip. So this is a DRAM cell. You have a word line over there and a bit line, and you have a capacitor. You have an access transistor that is connecting this capacitor to the bit line. And this is a volatile memory technology. This capacitor leaks from many different paths, and as a result, you lose charge over time. And there is this phenomenon called DRAM disturbance. When you access a DRAM cell very rapidly, repeatedly, frequently, then you can exacerbate the charge leakage in nearby cells. And as a result of that, you can observe bitflips. Okay, this is a cartoonish picture of how a DRAM subarray or DRAM array looks like. So it's organized in two-dimensional array as rows and columns. And internally, we access them in a DRAM row granularity. So let's say we want to access data at row 2. We need to first open this row 2 and then perform our accesses to different parts of this row 2. And then once we are done with row 2 and we want to access other data in other locations, we need to close this row. If we do this operation many times, open, close, then you observe bitflips in the other adjacent rows that you didn't even access. And we call the row that we keep accessing aggressor row, the rows that are affected victim rows, and this access pattern is called hammering. Okay, so this can be used for breaking memory isolation. This was showed as a widespread phenomenon in real DRAM chips in 2014. And just like 1 year later, Google's Project Zero showed a real system attack inducing bitflips in page table entries so that you can hack the system, get the root privileges. Following this, there were a lot of papers in the, okay, there's some delay, in the field, but I'll just show one paper, like 10 years fast forward at 2024. There's this paper from Google that claims to break the known best countermeasure of Samsung to RowHammer after 10 years. So it's still like a problem in that sense. And there are a lot of works in the field, in the academic literature. If you go look, you can see that RowHammer is possible via running some JavaScript code on mobile devices, using GPUs, used in network accesses on remote machines. You can use it to leak information without actually hacking the system, getting the root privilege, or causing a malfunction in the system. You can make your bitflips really targeted to change weights in your neural net so that their accuracies can go from around like 90% to 10%, for example. So these are all the works that are like you can find in the literature from various different groups. And there are works that show that ECC, error correcting codes, are not really very effective against RowHammer attacks because it's not uniformly distributed necessarily. You can target some bitflip locations, and there are works that bypass that. And there are works that show that in an 8-byte data word, you can induce up to 7 RowHammer bitflips when there are mitigations intact. So it requires a strong error correction capability to address that kind of issue. Last year, this paper showed that even in DDR5 now, with the increased refresh rate, with on-die ECC, with RowHammer mitigation mechanisms probably implemented, you can get non-zero bitflips. And there are more works coming up this year, actually, that show that you can even have more. Okay, so this is a problem, and we want to solve it. What is the solution? It's something really simple, actually. Once you detect that this is your aggressor row, you just need to perform an operation called refresh on these potential victim rows before they observe bitflips so that you can get rid of that. This is very simple. But the challenge is technology node scaling. As we scale technology nodes, cells get smaller and that get closer to each other. And as a result, you observe bitflips at much fewer activation counts, much smaller activation counts compared to before. There's a strong scaling factor here. And DRAM cells become increasingly more vulnerable to read disturbance. And as a result that, these works show that existing solutions are either prohibitively expensive or ineffective going forward, or they become in the future. And we need efficient, scalable, and comprehensive solutions to that, right? Okay, so I'll just like switch gears lightly and talk about an ideal world in my mind. How we can maintain memory, how can we make memory more reliable and fast and energy efficient in a better way. This is a paper that we published in last year, Micro. It was on archive for 2 years before that, actually. I'm just gonna talk a little bit about that. If you attended this honors keynote this week, he also highlighted this work a little bit. So this is what we have in our traditional memory system today. So we have the memory controller, which is part of the processor chip, and it sends commands to the DRAM chip. So the memory controller has fine-grained control on everything. And every nanosecond is defined by the memory controller. And DRAM chip just obeys what the memory controller tells. And there is data going back and forth in between. So what we want to do is to give more freedom to the DRAM chip so that when such things like RowHammer happens, DRAM chip has the flexibility to implement different maintenance mechanisms to get rid of, alleviate that problems. And the modification in the interface is a negative acknowledgement signal from DRAM chip to the memory controller so that DRAM chip can ask memory controller to just like back off a little bit, give me some time. I'm gonna do some maintenance operation on a region of memory, and it can work that way. And the memory controller accesses other locations meanwhile. Okay, so in this work we had like 3 use case studies. One of them is like we implemented the regular maintenance operation, DRAM refresh inside the DRAM chip. We implemented some RowHammer protection mechanisms and memory scrubbing that shows that we can achieve all the good benefits of the works in the literature without additional changes to the interface. So it makes the adoption of new ideas much easier in real DRAM chips. So yeah, there's a huge talk about it. I'm not gonna talk about it more. And there's this references, and I already shared the slides. I think it will be online somewhere, right? Okay. So while we were busy with this, industry also didn't stop. So there's a huge effort and energy spent on the industry side towards solving RowHammer. So JEDEC is the Joint Electron Device Engineering Council. It's the body of like representatives from many companies that define the standards of the memory devices like SSDs, flash memories, DRAM, and they formed a task force to address RowHammer. And manufacturers also changed their attitude. In the very beginning, they were like in more like denial kind of attitude that they were claiming that RowHammer wasn't the problem, and then they changed to a more solution-oriented attitude. And we saw the first solution from a memory company in 2021 called Silver Bullet Technique. Okay, and then we have like more papers coming up from Microsoft, SK Hynix, Samsung, NVIDIA, and Google. Yeah. So there's more works going on in the industry for that. And JEDEC released like 2 different documents as like guidelines of how to mitigate RowHammer in your system if you're designing your system. And finally, last year, they came up with this update called PRAC in general. It's the first promising update a decade after the discovery of RowHammer that can solve the issue if implemented correctly. Okay, with that, I'm gonna go dive into more details of this PRAC mechanism, and we investigated how it works, its security, how is its security, how is its performance, energy. I will dive into all those details now. But so far, are there any questions? I'm just like going through the slides. Okay. Yeah, let's start with this work then. So this is a work that we first like published the early version of that in DRAM-SAC. It's a workshop focused on DRAM security, as the name suggests, and it's part of ISCA. So we wanted to do that because this was like the very first meeting of like researchers after that release in April 2024. And we actually discussed a lot across different groups in that DRAM-SAC workshop. And we even realized that our security analysis was not completely correct. We even like released an update after that. I think this collaboration is really important. And then extended full version of this work, including an alternative implementation of PRAC, is published in HPCA this year. Okay. Okay, yeah. So now I'm going to talk about the 2 mechanisms that are defined in the JEDEC documentation, but I have to do a minor change to JEDEC documentation in my description because some terms are used for like to identify different things, and we had to introduce some new terminology. So one of them is this periodic refresh management. So there's a command called RFM. It's refresh management command, and there is a mechanism described in the JEDEC document where the memory controller periodically sends refresh management commands to the memory controller. And the other mechanism is called PRAC, per row activation counting, and like this original name is per row activation counting, but a key part of this mechanism is the backoff signal, so alert backoff signal. So we added that to the name as well. Anyway, okay. So let's go with the first one. So here we have our processor chip and then memory chip, and to access data, the processor needs to activate some rows, to open rows. And these activates happen over time. And we have like multiple banks inside each of these chips. And okay, I didn't have the backup slides for that. Anyway, so you have a counter per each DRAM for each DRAM bank inside the processor here. So you track how many activations each bank gets, and in a bank you have tens of thousands of rows. So it's a really coarse-grained tracking. And in a DRAM chip, you have around like 16 banks or 32 banks, depending on the standard that you're working with. Okay. And after some number of activations, the processor sends a RFM command. So this RFM command tells the DRAM chip that it has a predefined time window where it can perform the maintenance operations like refreshes. So the DRAM chip itself should also track the access patterns and then identify which rows are potential victim rows and refresh them at this point. Okay. Yeah. So this is the periodic refresh management mechanism. And then let's move to a more important one, per row activation counting. So this, so here the proposal is that we achieve high density of storage inside the DRAM technology, right? So why don't we use the DRAM technology itself to keep the metadata about the access pattern, which is how many times we access each DRAM row. So these are this is your DRAM array again. So you store some data in your DRAM row, and then you add a few bits. So this green part is around like 8 kilobit in a sense. Like it can be different, of course, but like some ballpark number. And you put a few bits next to that, like 8 bits, 10 bits, something like that, to each row. So you make the row a little bit wider. And as a result, you can put the counter value there. So so by doing this, you can accurately track how many times each row is activated. Okay. So this row is activated like 1 times, 2 times, 3 times. So you just like keep updating the counter like that. Okay, so there is more details into this mechanism, but first I need to take a step back and give a little bit more background. So here, this is another cartoonish picture of a DRAM array. So we have the DRAM cells over there, and these blue things are the sense amplifiers. So to open a row, we perform this operation called activate that asserts the word line and connects the cells to the sense amplifiers in the bottom, right? And then we perform the read-write operations. And then we perform the precharge to close the row. And activation and precharge are time-consuming operations. So when you activate, you need to wait for some significant amount of time, around like 10 to 15 nanoseconds, and then precharge similarly in regular usage. And there are some timing parameters, timing constraints in the standard that limits the time that you need to wait for. Okay, so when we access a DRAM row, we don't access the DRAM row for the sake of accessing it, right? We need to serve some request. So when we activate a row, we need to immediately access the column that we are looking for so that we can serve it back to the processor chip. So now you open the row, you perform your column accesses, you fetch the data from the DRAM chip, send it to processor, and then now you're done. And you need to access another row, but you didn't update the counter yet. So what happens is that, so in this mechanism, you need to read this counter value outside of the DRAM array, increment it by 1, and then put it back. And you need to do this operation while you're closing the row. And as a result of that, your pre-charge latency, meaning that the time between the time that you close the row and then you open the next row, this latency increases by 140%. So it's like a lot of overhead when you think about the access latency. And this is how the timing parameters change on DDR5 when you enable crack mechanism. So these are the values on the left. These are like absolute delta values, like how it changes, and these are the normalized values. So it reduces some timing constraints. So it reduces TRS, for example, because there's some like overlapping latencies while you're updating the counter. You can let the charge restoration of other cells going on. But the essential part is like overall the row cycle time increases around 10%, and the row close time increases by around 140%. Okay. So we perform an activation, another activation, another activation, another activation. We increment row count, and then we reach to a value here that you define. I'm going to show how you define it. And when you reach to this value, then we call it back-off threshold or alert back-off threshold. DRAM chip asserts an alert signal back to the processor chip. And when this happens, processor is allowed to perform normal traffic for 180 nanoseconds from that moment. So it can send more activation commands, for example. So you need to account for the worst case in case it sends activation commands, you don't know it. And then based on your crack mechanisms configuration, the processor chip sends this refresh management command back to DRAM's chip, from processor to DRAM chip. So it can send like 1, 2, or 4 RFM commands back to back. Let's say in this example, we send like 2 RFM commands. So this gives a huge amount of time to the DRAM chip to perform the refresh operations. And as a result, you get the rows refreshed. But after this recovery period, there is a delay period, also defined in the standard, that for like some number of activations, the DRAM chip is not allowed to send another backoff signal to the processor chip. So this is also important. This will also become important in the implementation details. Okay. Why doesn't this work? Okay, I'll just move to the security analysis and how you configure this crack mechanism. So you want to configure this mechanism in a safe way, right? So you do not want to have this mechanism, have this overhead, and then bitflips still happen. So you need to analyze how you need to configure it, and you need to define the worst case access pattern. The worst case access pattern we found is the wave attack that we call it. It's also referred to as fainting attack in other words. The strategy is like you start by in the beginning of the attack, you keep a low profile and you access to many different rows, and you increment their activation counts until a point just below the backoff threshold. So you do not trigger any backoff, but you prepare all the rows, like you load them up, and they're ready to, like, after one activation, they will trigger backoff. But you just keep them at that point. And then after that, you just like activate each one of them like once. That will create a lot of trouble in the system, a lot of backoff signals, and a lot of maintenance. So for that, we have 3 parameters. One of them is the starting row set size, like how many rows we will prepare for this attack, and what will be our RFM threshold, like after how many activations we send an RFM, and what is our backoff threshold for crack. Okay. And this gives us the worst possible activation count we can achieve for a given configuration. So here are some results. Okay, what should I do with this? Okay, I guess it's good. It's good. Okay. So here, okay, I'll just stay here for the slide. So here on the x-axis we have the RFM threshold. How much it increased. So we increase it from left to right. And then on the y-axis, we have the highest activation count we can achieve as an attacker if the RFM threshold is configured that way. And different colors show different sizes of the row set in the beginning. So as we go from left to right, we have less frequent RFM commands. So like it's lighter kind of maintenance. And on the y-axis, lower is better for us. So if we go for like a 256 activations as the RFM threshold, and we have the starting row set size as like 2000 rows, for example, we can reach to an activation count similar to like 2048 here, like very close to that. So let's say our RowHammer threshold is 1024. So after 1000 activate, let's assume that your DRAM chip experiences bit flips after 1000 row activations, meaning that for this configuration, like the range below that red line is safe and above is unsafe. So if you go with the 256 threshold configuration for RFM mechanism, I can use 2000 rows and then perform this attack, and then as a result, I can exceed the RowHammer threshold. So it's not unsafe. So we want all the bars to be below that RowHammer threshold. And for example, here, if we want to protect against a RowHammer threshold of 128 activations, we need to send an RFM command after every 8 activations, which is quite frequent, and it causes a lot of performance overheads. Okay, for PRAC, things look a little bit better because it's more fine-grained tracking. And here we have like different PRAC configurations. So PRAC 1, after you get the backoff signal, I told you that the processor sends 1, 2, or 4 RFM commands back to back. So PRAC 1 is like 1 RFM command, PRAC 2, 2 RFM commands, PRAC 4, 4 RFM commands. And we show that if you, so this is the like lowest extreme, right? So we set the backoff threshold to 1 activation. So after each activation, we send a backoff signal, something like that. And as a result of that, when we conduct a wave attack, we can achieve an activation count of about like 32 here, for example, for PRAC 1, and 19 for PRAC 4. So if you go with PRAC 4, like PRAC 4 configuration, and if you set the backoff threshold to 1 activation, which is really aggressive, you can protect against the RowHammer threshold of like 20 activations. So we conclude that PRAC can be configured as a secure mitigation mechanism until the RowHammer threshold of 20 as the like lower bound. Of course, this is like super extreme if you think about the access patterns and how much maintenance overhead it will incur. So that's the next part. So what is the impact of this security mechanism on performance and energy? So we conduct some simulations and we evaluate different mechanisms, periodic RFM, PRAC in different configurations, like PRAC N stands for NRFMs for each backoff, as I said earlier. And there's also an additional mechanism in the JEDEC standard called PRAC plus PRFM. It's basically like combining both. You send RFM commands periodically, and then you also have backoffs. And when backoff comes, you also send 4 RFMs back to back. Okay. So here are some performance results. On the x-axis, we have the RowHammer threshold. From left to right, the RowHammer vulnerability increases so that the RowHammer threshold gets lower, and it goes down to 20, right? And there are some bars here that are like just showing the performance overhead, but they are not safe. So it's these like 2 bars, the green bars. So ignore them. Anyway, they are not very important. So as a more realistic threshold for today's systems, if you go for a threshold of 1024 activations, we observe that PRAC's, this is PRAC, right? Yes. PRAC's performance overhead is around like 6%. I had a slide before this. Anyway. And then, okay. I just realized that I'm using still slides, but it's okay. Okay, if you go for like very low RowHammer thresholds, then your PRAC's overhead increases until 64. It increases slightly and then drastically. So those like lower thresholds than 64 are still like quite dangerous performance-wise. So we identified 2 major problems or limitations, let's say, with PRAC. One of them is increased critical DRAM timing parameters. As I said, like the TRP, the pre-charge latency increases by 140%, which is not very pleasant, and it incurs large performance overhead. And the vulnerability to the wave attack actually requires us to configure PRAC mechanism for very low thresholds, for the backoff threshold, and it results in poor scaling. So we could have actually scaled it better if we wouldn't be if we would be more resilient against wave attack. And we have solutions to these. So our first solution is to alleviate the additional latency of updating the counters. We basically leverage subarray level parallelism to concurrently update the counters while serving DRAM accesses. And as a result, we do not incur increases in critical timing parameters. And we prevent wave attacks by alleviating a restriction in the standard, where that after the DRAM chip sends the backoffs, and then processor sends the refresh management commands, and then there was a delay period, and that delay period is causing the issue of vulnerable to the wave attack. And the idea is to allow the DRAM chip to send as many backoffs as it needs, so that there can be like many refresh management commands back to back, so that once you get into that phase, you can refresh all the victim rows at once. Okay, it will cause you some latency, but it will not make you vulnerable against the wave attack. Okay, so let's go with concurrent counter update. So what we propose here is that, so this is the regular subarrays in our DRAM array. So DRAM array is chopped into smaller pieces called subarrays, and there are like row buffers and some isolation in between. And there are like many of these in a DRAM array. So each subarray has around like 1,000 rows, and tens of thousands of rows are there. Anyway, around like 100 subarrays are in a DRAM array. And what we propose is to add another subarray, which is much smaller than a regular subarray, just to store our counter values. So whenever we activate a row, in parallel, we can access to these counters, and we can also implement the increment circuit over there, which we model in the paper. I'm not going to get into details. And by leveraging subarray level parallelism, we can overlap the latencies of this counter update and DRAM access operations. And this gives us, this alleviates the performance issues, basically. And the counter subarray incurs around like 0.5% area overhead per byte. So it's just a number over there. Subjectively, you can say it's too much, it's too low. It's okay. So this is the analysis. Like we just wanted to put the trade-off there. And you have the counter subarray activating rows. So whenever you activate a row, there's a chance that you need to activate another row in the counter subarray, and it increases the energy overhead. Like if you look at the memory access patterns and get the like average energy overhead of activating that other row, because sometimes you don't need to. It increases the activating energy of activating a row by 19%. And actually, there's another paper published recently in, wait. It shouldn't be HPC, but anyway. I guess there was something wrong over there. Yeah, it's a concurrent paper in that case. Okay. So that builds on our earlier proposal that addresses this energy overhead as well. So we are going towards a better direction than, I guess, what the JEDEC proposed in the, initially. Okay. So this is the other part of the mechanism. So this is what we proposed. I actually already talked about this. So we want Chronus to be able to, or PRAC, to be able to dynamically control the number of refreshes needed. So it should be allowed to refresh as many rows as it wants at once. Okay. And it shouldn't have the delay period after that. So yeah, this is the time diagram that I'm referring to. So Here you still have the normal traffic, so it doesn't like quickly interrupt the memory accesses. But when it comes to the recovery phase, it doesn't have to be necessarily limited to like 1, 2, or 4 RFM commands. It can be like many RFM commands here, and we just like remove this delay constraint, and we evaluate the performance and energy of that, and these are our comparison points. So these are some mechanisms in the literature and also from the JEDEC documents. Yeah, I need to take I need to pause here and make a acknowledgement to this paper. It's a CAL paper that recently appeared a few months ago, I think, from Janawan's group that actually looked at our implementation of PRAC in our simulator and found out some bugs. And they showed that the performance overheads were not as bad as what we thought. By the way, yeah, so after that, we actually went back to our implementation, like double-checked everything, and indeed, there was a bug. And we released a patch into our simulator, and then we updated all our results. So the results that I showed you so far are the updated results. So before we were talking about like a 10% performance overhead on average for like 4-core performance. And then now it's like around 6% based on our simulation results. Of course, like there is a discrepancy across like different evaluations of these papers. Their paper it measures these performance overheads on real systems, which have quite large caches, and the workloads become like less memory bound. We just like in our simulation environment, it's like a common practice to keep the caches to some level so that you can see the effects for memory heavy workloads. So there are some like configuration differences that cause this discrepancy. So I guess like now we are safe having like both results in the literature. If you want to go for like real system, you have the results. If you want to play with like some hypothetical system in a simulation environment, you have the results. So I'll just continue with the 6%, but this is like a disclaimer. There's nothing wrong with those results. You can go to that paper and see the configuration and the workloads and the real machines that they have, and everything checks out. Okay. So with that disclaimer, I can continue with the system performance evaluation. So we reduce the RowHammer threshold on the x-axis again, and we observe that Chronus and Chronus PB, it's like two variations of Chronus. They reduced the performance overhead of the original PRAC from 6% to like less than 0.1%. It's purely about the reducing the or alleviating the latency increase for pre-charge operation. And this is for like a more realistic threshold for today. And as we go forward, we have like we also observe that Chronus performance goes bad, but it's not as bad as the original PRAC implementation. Okay, so here we look at the energy, and for the realistic parts, around like 1024 activation count threshold, we don't have much energy overhead, and then basically it's like on par with what PRAC was proposing, and as we go for lower thresholds, it increases quite significantly, but not for Chronus. And it's because of the scalability issue due to like wave attack vulnerability. Okay, so in summary, Chronus reduces PRAC's performance overhead, and it concurrently updates counters and dynamically controls the number of refreshes. I think I took way more than I was intended. So, but yeah, there are more details in the paper. I'm not going to go through them. And this is the full paper with the archive link and QR code there. And in conclusion, we analyzed and characterized the JEDEC specification and showed the security, performance, and energy overheads of the new crack mechanism. Showed that identified two fundamental limitations and proposed some solutions to those as part of the mechanism Chronus. And our implementation is open source on GitHub. You can play with that. It's also in the main branch of Remulator too. So you can, yeah, if you use Remulator, you already have the implementation. Okay, so this is the Chronus paper. And in my plan, I wanted to talk about another aspect of RowHammer problem. I'm not sure how we are doing with time. Should we continue? Maybe I can ask some questions at this point. Are there any questions? Yeah, we can just go ahead then. So I'll cover this paper relatively more quickly. So BreakHammer, the name comes from the structure, breakwater. So, you know, I guess you have a lot of them here in Korea. You're like very close to the ocean, right? And in ocean, you have really strong waves. And you also want to have your ships, your boats stay in the dock, right? But not affected from the large waves of the ocean. So you construct a structure. It's like a civil engineering term called breakwater. So you put like a huge wall inside the water, so it breaks the waves coming from the ocean. And inside the dock or marine, you have like a more calm water. And then it allows you to reduce the maintenance costs of the dock itself and the boats inside the dock. So this is coming from that analogy. Basically what we do is that when the RowHammer access pattern comes from the processor, we put a filter over there called what we call BreakHammer, and it reduces the hammering access patterns when it comes to the memory controller and to the memory chip. So you do not have, you do not let the attack to go as aggressively to the DRAM chip, and as a result, you can reduce the maintenance costs. So this is the main idea of this paper, and it's published in Micro 2024. So when we look at how we perform RowHammer mitigations, we have many methods actually. One of them is refresh, the other one is row migration, another one is proactive throttling. You can just make the list much longer with many different ideas. The most popular two in the literature are refresh and row migration. So we focus on those two in this work. And what happens is that, so this is your processor, this is your DRAM chip. You want to access the DRAM chip, and you want to activate, right? But if there's a maintenance operation going on in DRAM chip, you cannot access. And this is the problem. And while you're refreshing kilobytes of data here in DRAM chip, like one row is like 8 kilobytes, 16 kilobytes. While you're doing some maintenance over there, you block accesses to the whole bank, gigabytes of data. So this is not good. And we want to reduce the occurrence of this as much as possible. And here you have a user in your system using this core, and it accesses memory through this memory controller. And there's another user here, which is an attacker. And it can cause, it can craft an access pattern that is performing RowHammer accesses. And the purpose is not to induce bitflips, but to trigger the existing mechanisms down there so that they will create a lot of latency, a lot of congestion in your system, so that your user will be unhappy. So it's more like a denial of memory service or memory performance attack kind of scenario. So the operations that prevent RowHammer reduce DRAM bandwidth availability and block access to memory. And our goal is to alleviate that by reducing the RowHammer mitigations performance overhead. And how we do is that we reduce the number of RowHammer preventive actions without compromising the system robustness. And how we do that is we try to detect who is this guy, and we suspect this hardware threat and reduce its memory bandwidth usage. Okay, so there are a lot of details here. I'll not go into all of them, but you have, like in this time line, you have a refresh here, a RowHammer preventive action, another RowHammer preventive action here, and you have some activations in between happening. And you need to track from which hardware thread those activations are coming. And once you do that, you can attribute some sort of score to each thread. And once you have these scores over an extended period of time, you can observe like which user, which hardware thread is an outlier, which one is like presenting some anomaly in the system, and then you can reduce its memory bandwidth usage. So I'm not going to get into details about detecting it. It's quite straightforward. It's the most naive thing that you can think about. It's just like count the activations and then get increment some scores to each thread proportional to their number of activations. And we integrate BreakHammer with 8 different RowHammer solutions to show that we can implement it with like a lot of RowHammer solutions. So there are definitely more than 8 solutions in the literature, but we didn't like exhaustively implement everything. But if you trust me, if you believe me, I can say that it works with all of them. Okay, and we can discuss if you don't believe me. So when it comes to identifying suspect threats, what we do is that, let's say we have the number of threats here. It's a cartoonish picture, I know, but just to give the idea. We have a minimum score. We just like don't care about the threads that access memory really rarely. Okay, and then above this minimum score, we get the maximum deviation from the average of these. So we get the average of these threads as scores, and then we find the maximum deviation, and then we have another threshold there. If the deviation is larger than some threshold, then we say that, okay, yeah, there's something fishy going on with this hardware thread. And as a countermeasure, what we do is that it's also quite straightforward, actually. Our scope is based on these systems that have some shared loss level cache, which is very common. And if you remember from computer architecture, if your data is not in your cache and you need to go to memory and bring that data, you need to allocate a misstatus hold registers here. So it's like MSHR, or I guess they were also referred to as like cache line registers, cache miss registers, those things. So there are those structures that you need to allocate that limits the number of requests at a time that you can have going to the memory. So in normal case, there's no limit for any hardware thread. Like anyone can allocate like all of those registers. But once we detect some anomaly, we put a limit to the thread that we suspect. So it cannot allocate many of those registers, meaning that its requests do not go to the main memory, to the memory controller. And yeah, cache miss buffers. Yeah, okay. And then as a result, let's say think of this as like an epoch-based mechanism. In the first epoch, we suspected a thread performing a RowHammer attack, and we just like slowed it down by limiting the mishold registers. And then in the next window, let's say this thread didn't perform that kind of access patterns. and it just like behave. And during this window, it's still throttled because like in the previous window, it was suspected. And then after this epoch, the memory bandwidth usage is restored for this thread, and then it's allowed again to use whatever it needs. Okay. So we look at the performance and energy consumption of this mechanism, and we compare it to the original proposals. And so for each proposal, we implemented them with BreakHammer and without BreakHammer and compared the results. And we have like a lot of workloads here. And we have two scenarios that we did the evaluation. One of them is under attack. So this is for crack. Take these results with a grain of salt, because this was done before the bug fix, and we didn't have time to update them yet, but we will update soon. So as your RowHammer threshold goes low from left to right, the performance overhead you can get from crack as a result of this malicious memory performance attack increases quite significantly. And actually, there was some annotation to some numbers. Okay, so this blue one is no BreakHammer and orange one is with BreakHammer. So, okay, at a RowHammer threshold of 128, if I conduct a memory performance attack, I can slow down this DRAM subsystem by 34x. And when I use the same mechanism with BreakHammer, I can reduce the performance overhead by 80%. So I told you to take the prac with a grain of salt, but the other implementations are correct, so there's no bug there that we know yet. Please, by the way, feel free to go into Remulator's implementations and find bugs and report us. We really want that. Anyway, so for each mechanism, you can see that the orange curve is way below than the blue curve. So it means that you can send all those requests, creating all those like huge waves in the ocean, and then after BreakHammer, you have a much calmer kind of access pattern, and the overheads get much lower. Okay. Okay, this is the same scenario for the preventive action count. It's like tightly related. And we look at the memory latency curves. So maybe I can just skip this data. But this is very slow. Okay. So similarly, we also improve the average memory access latency. And when it comes to the energy consumption, okay. When it comes to the energy consumption, BreakHammer reduces the energy consumption quite significantly as well. And sometimes the energy consumption goes below 1.0, meaning that, since you're now throttling some malicious threat, you're actually preventing it to use memory bandwidth and cause a lot of activations, a lot of row buffer conflicts. And it's a time-consuming operation to activate temperature rows, and you get rid of all of them. Compared to baseline, you can get some energy benefits as well. Okay. That's pretty much it. And for the interest of time, I'm not going to get into more details. For the no attack case, we show that we do not have very serious side effects. This is also a claim that we need to make really carefully, actually, because this is limited to the test cases that we could come up with. So tomorrow we can come up with a test case that actually, in a no attack scenario, cause BreakHammer to make things much worse. We do not know it yet, so more work needs to be done. And we have a lot more in the paper. We have, I just invite you to take a look at the paper. Okay, and in conclusion, we propose this BreakHammer mechanism that observes triggered RowHammer preventive actions and identifies which threat seems like a suspicious threat that is performing a memory performance attack. and reduces the memory bandwidth usage of the suspect threads. And it's also open sourced on GitHub and also in the main branch of Remulator. Okay, with that, I guess it's, yeah, we're almost, yeah, we are out of time, I guess. If I have like 5 more minutes, I'm gonna talk about like some future directions a little bit. Okay. So going forward, I want to explore more directions, not really limited to RowHammer, but more towards enabling better scaling in systems in a secure and sustainable way. So, you know, hardware-software co-design is something that we keep using in our research for like many years, and it's also already proven that it has many benefits when it comes to performance, energy consumption. But it's not really very well used for security purposes, in my opinion, and we can do more things. Here's an example slide that I'm not going to go through, but you can check it later, I guess. Basically, we can extend like whatever we have for RowHammer or like side channel countermeasures, we can extend them to more operating system level. We can cooperate the software, the operating system, hardware all together, and we can find better solutions. So maybe I should talk about it actually. For BreakHammer, for example, we can identify the hardware threads. But one weakness of that work is that I know which hardware thread is doing suspicious activity at this time of the execution. And then a context switch happens. And then another software thread gets that hardware thread. And my previous hardware thread goes to some other location. Maybe it is killed. And then the same user spawns another thread that does the same thing again. So we don't have these concepts in the hardware level that allows us to, you know, identify where is the source of the problem, which user is doing that. And we can only identify it successfully with an integration with the operating system, hypervisor, all that. Okay, so another direction is data-centric security. I showed you this slide from Bill Daly in the very beginning. Memory accesses are consuming a lot of energy. And to address that, there's a huge momentum. If you look at the conference proceedings as well, you will see that there's a huge momentum towards data-centric computation for better performance per joule per area. And processing, memory, and storage are two promising computation paradigms, but they are mainly used or studied from the performance and energy aspects, not really from the security aspect that intensely. There are some works coming up, but still in the state of the art, in industrial standards, we have our security practices in a more processor-centric way oriented. And once we can enable these similar practices in a more memory-centered or storage-centered way, then we can enable lots of better scaling and a lot more reduction in energy consumption as well. Yeah, there are already some works doing that, but as I said, like it's not really exhausted yet. And we have other aspects of data-centric computation. So allows trade-offs change when you move from processor to main memory. For example, side and covered channels can be easier. There were like some works published in this year. This is one of them. Another one appeared in Micro. Yeah, there are more things that needs to be restudied again here. I'm also interested in two particular family of applications. One of them is agent-based simulations. The other one is genomics. I find these applications really important because they are like very related to human health, and it's one of the like major problems that we have today that we cannot really solve. Like we are not immortal, right? So there are way more room for improvements over there. Okay, so as common characteristics of these workloads, they use excessive large amount of data. They're usually run in distributed and shared environments, and data integrity and confidentiality and privacy, all of them are really important for those applications. and these are not really tackled well so far. So I want to do all those. And last thing, this is, I guess, the last slide, that we need better understanding of the failure mechanisms in our chips so that we can further enable technological scaling. A generic question that we need to answer is, what is the worst case for a given system? We do not know. It's really scary. Failure mechanisms depend on many conditions, and they can be observed only probabilistically and often, like most of the time. And post-manufacturing testing is very expensive, and it cannot cover all the conditions. You need to own the chips. You need to dedicate those chips for testing. You cannot use them. So it's like a lot of economical overhead over there. And we need better methodologies and infrastructures to fundamentally solve this problem. I think this is what we need to do in the bare bottom. We need better online testing methodologies that can run on chips in runtime. I'm not talking only about memory chips. I'm talking about processors as well, or the storage chips, flash chips, everything. Whatever you can think about, like GPUs, accelerators, everything. To understand the vulnerabilities of these chips, meaning the vulnerabilities in the device level and vulnerabilities in the architecture level, the security issues. To identify all those, we need a more aggressive, more rigorous testing, and it's not feasible at all in a lab environment. So we want online testing methodologies. We want to develop them. We want automated reverse engineering tools so that we can offload this whole testing work to the users and crowdsource the data collection. This is something I really want to do, and I wanted to mention that here as well. So if it's interested, like any of these interested, if you are interested in any of these, please come talk to me. Okay, so we have some examples of the good offline testing tools, but yeah, they're not really plug and play in runtime. Okay, I'd like to conclude with my goal: systems to scale securely and sustainably as chips get denser and many users share these systems. This is where I am located again, and I'm looking for motivated researchers in different levels. Please contact me. This is the end of my talk. Thank you very much. I can get your questions.
I have two questions. One is simple, and the other is more philosophical. So first one, for Chronus, so adding a new subarray for the counters, could it cause a new vulnerability, more like hammering on the counter subarray things like that? That is the first one. And the second thing is that for the RowHammer, so the introduction of Onda ICC and DDR5. So people sometimes have reporting about the decreasing demand, decreasing trends of the RowHammer threshold because in DDR5 it became more difficult to observe bit errors, although some research has published. So how would the future trend for the RowHammer threshold will be? So it will simply keep decreasing, or DRAM vendors will develop a new mitigation scheme to make it the kind of more stronger ECC and other things. These are my questions.
Yeah, great questions. Thank you very much. So I'll start with the first one. In Chronus, we implement that subarray that keeps counters. It's a DRAM array. It's also vulnerable to RowHammer. We need to protect that as well. So since it's a specialized kind of subarray and it's much smaller than the other ones, we propose to protect it in a few different ways, like we just discussed it in the paper. One of them is you can implement a mechanism called Rega over there. That's from Kaverazavi's group. Basically, whenever you activate a row, first of all, so in that small subarray, you have the array of sense amplifiers, and you implement an additional array of latches as part of that subarray. you fetch the data. So you activate the row that has your counter. The data comes to sense amplifier and you latch it. And then sense amplifiers are disconnected than those latches after that point. And you can perform, like, while your row is still open down there in the latches, you can refresh rows in that counter subarray. So if the subarray is small, we can do that, for example. Another thing we can do is we can put more isolation. So we can put the rows like more distant from each other. Or we can allocate some guard rows in another work called DRAM. And actually, there was this Citadel work in this micro that is based on this isolation. Yeah, so we can do something like that as well. Like there are like different methods I guess we can implement. Yeah, we discuss all that in the paper. If you have further questions about that, maybe I can get that first, and then we can talk about the second one.
Do you have some questions from the audience?
Yes.
Thank you for your presentation. My name is Boyer Choi, and I'd like to
Yeah.
I have one question on the BreakHammer.
BreakHammer, okay.
The main idea of BreakHammer is reasoning some attackers, breaking core of system about memory bandwidth. Your idea is attacking maybe an attacker and give low available bandwidth, and maybe there's some misleading about some attack. They're not attacker, but you give some low available bandwidth.
Mm-hmm.
There's some problem with data center level, like giving some virtual machine to any user, and someone is not a attacker, but they suspected to attacker, then get a low bandwidth. Is there any problem?
Okay, I think we're talking about different attack models here, or threat models. So there can be a RowHammer attacker that keeps a low profile. So you can actually hammer rows in a way that you have like your MPKI is lower than what MCF has, for example. And so a benign workload can be more memory intensive than RowHammer attack. For those, so it's a bit out of scope of BreakHammer actually, and here's why. So the RowHammer attack can happen, and we already have the RowHammer mitigation mechanism over there, like those 8 mechanisms, for example, like any of them, or PRAC, like PARA, whatever. So they're already there to ensure that data integrity is not compromised. So they already address RowHammer attack. So what we more care about is that if an attacker wants to conduct a memory performance attack, a denial of service, by using the RowHammer mitigation mechanism. So we want to avoid that. So in that case, the memory performance attack should be like more memory intensive than the benign workloads. Yeah, sure.
So we are already 15 minutes behind the schedule, so can you please go offline and question?
Oh, okay.
Thank you, Dr. Drive, for this kind and thorough and unorthodox presentation. Yeah. So let's thank the speaker again.
It's my pleasure to be here. Thank you a lot for hosting.
This is the end of the seminar.